In the last lecture, I have given you a broad overview of all the smart materials which are generally used. But in this lecture, I would like to focus on a very particular smart material which is known as piezoelectric material and which works on the principles of piezoelectricity. So, these are the things that I have a plan to cover. First, I will give you a little bit of history of piezoelectricity, because once you know the history, the evolution, then it is easier to keep it in your mind about the how the developments are progressing in this field. Then I will talk about piezoelectric materials, and I will tell you how to prepare an actuator using one of these piezoelectric materials like piezoceramic powders. Also, I will talk about the constitutive relationship, which is essentially the stress-strain relationships, of piezoelectric material, and then I will talk about the piezoceramic polymers and composites, and finally I will talk about bimorphs and piezo stacks. So let us first start with the history of piezoelectricity. Now, piezoelectricity has a long history in the sense that about all the modern advanced materials that we are today working on, and that is very relevant in today, piezoelectric material is actually the oldest among them. And the word piezo means actually pressure. So piezoelectricity is, in other words, it is electricity from pressure, which was discovered by Pierre and Jacques Curie. You have heard about the Curies, in many contexts you will heard of them, their contribution to crystallography, their contribution to radioactivity studies. These are all very, very famous. So Pierre and Jacques Curie's work in 1880, when they were actually working on some of the crystals like tourmaline crystal, and they found that you can get electricity out of the piezoelectric material. That was the first of this kind of a discovery. Then at that time there were actually two sources of electricity that was known to us. So that is, one of them is contact electricity, which is actually so called static electricity that gets generated from friction, and the other one is actually pyroelectricity, which is electricity that is generated from crystals while heating, because that pyro means heating. So contact electricity, heat generated electricity, and then in that series they found out pressure generated electricity. Now then, that was the first observations experimentally about piezoelectricity, and 1903 Pierre Curie got Nobel Prize on this particular thing, that pressure is generating piezoelectricity, which is also known as direct piezoelectric effect. After a few years, Lippmann, very interestingly, studied the same problem, and he has proved theoretically that if pressure can be the cause of generating electricity, then electricity can also create deformation or pressure in a crystal. That is, the reverse is also possible. This brought him another Nobel Prize in 1908. So that is known as the reverse piezoelectric effect. So we should know about these famous names in piezoelectricity: Pierre Curie, Jacques Curie, Lippmanns, Voigts, Langevins. I will talk about as and when these names will be coming up. The timeline, if you look at it, then the first is the direct piezoelectric effect, which was observed by Pierre and Jacques Curie, in which the mechanical force were actually generated electric charges. This was found one by one in materials like zinc blende, boracite, tourmaline, quartz, cane sugar, and Rossel salt. So quite a few crystals they found that they show this particular behavior. 1881, Lippmann suggested the reverse effect, and it got experimentally confirmed by Voigt in 1894. However, the engineering application took some more time, at least 30 to 40 years, when Langevin-Fast, used this principle in order to develop a sonar transducer. So this sonar transducer, it is actually made of a composite which is made of steel plate and quartz. So what you can do is that, suppose you have a steel plate and you have a quartz at the center, and then you apply voltage to this quartz. So you are applying voltage at a particular frequency. It is not a constant voltage, but it is varying, and as you are varying the frequency, you are getting vibrations in this particular steel plate. So that steel plate gets vibrated. As it gets vibrated, it actually generates waveforms on the water. Now suppose you have something here, okay, some enemy submarines which is here at this location, and the waveform gets hit from here. So it is actually coming back, each of the waveforms, and some of them are hitting this piezoelectric element back. What will happen then? This piezoelectric effect, because of the change of the pressure wave, it is going to generate a signal itself. So you can actually tap that and you can find out what is this signal, and that signal is going to tell you that whether there is an enemy submarine or enemy ship or anything like that. Okay, so that was the first application that Langevin has thought of, the piezoelectric effect. But starting the journey from there, today you have so many applications. For example, many of the gas lighters you will see will have this application that as you apply pressure, you will see the gas lighter sparks and generates a little bit of light which is good enough to actually ignite the gas. Like that, there are many applications that have come up from this 1881. Now, one of the reasons why all these later on, these applications were possible was actually because of the discovery of the perovskites. Perovskites, of course, it was first discovered in nature by scientist Gustav Rose, and in Ural mountains, in a small crystal, he found that it has a very interesting property, that it is not a single oxide but a ternary oxide, something like barium titanate. So that means it has two of the metallic types and one of the oxides. Now, perovskites, the structure of a perovskite is something like which has a tetragonal symmetry with dipole moment below Curie temperature. What is the source of this dipole moment? For example, if I look at this tetragonally symmetric crystal structure, we will see that the titanium is at the core of it, and the bariums are here at the vertices, and oxygens are at all the phase centers. Now what happens is that this particular structure is stable in a very small margin. The moment you try to deform the structure, suppose I am applying a compressive, I am deforming it, and then this fellow will actually get shifted from its location by a little bit, because you can never apply a very perfect force system. So at that atomic level it will get deformed, and that small deformation is good enough to disturb the structure so that you get an electricity out of it, because you see that titanium is electron giver and oxygen is electron taker. So this titanium at the center is just pseudo stable, and it will generate a dipole moment the moment you actually deform it. It was found out later on that it is not only barium titanate, but materials like lead zirconate titanate, lithium niobium, lead niobium, yttrium magnesium family, NH4 CD family, etc. All of them show this kind of piezoelectricity, and this piezoelectricity effect is actually much more pronounced than the piezoelectricity that was earlier found out in 1880s in materials like Russell salts, etc., or quartz for that matter. So here the deformation is much more, or the voltage generation is much more. We will talk about it in a comparison. But because of the predominantly the discovery of these perovskites, by the way, this name has come after a very famous Russian geologist whose name is actually Perovsky. In his name this is done. So the discovery of the perovskites actually opened a whole domain of new technology for smart transducers. Now, the dipole moments in a perovskite, if it is not polarized, is always random like this, very random. Each one of the atom will show a random dipole direction, which means that if you apply a voltage, because some are oriented, some are not, you won't get too much of a change in the deformation. On the other hand, if you apply a DC electric field and then at a very high DC electric field, and then you remove that electric field, you will get it partially aligned here, partially aligned. And once we do that, we call this to be the process of polarization. Then if you apply voltage, you will see a very sharp effect of piezoelectricity on the system. So how do we define this piezoelectric effect in the case of a three-dimensional, let us say, a system? So we have the core material to be piezoelectric here, as you can see, and there are two surface electrodes where you are actually sort of giving the polarization. In order to give the polarization, you have to do. Every time you actually purchase it in the market, you will see a black spot which gives the polarization mark. This is important and I will talk about it soon. Now you can define very easily, because it is a three-dimensional object, you can define very easily the three axes. So this is suppose the x axis or 1, y axis or 2, and z axis or 3. And we have to keep in mind that this point is showing that the polling axis is the z direction at towards this arrow itself. So that is the polarization direction. In this case, suppose you see this arrow here, then this is the polarization direction of the system. Now you can get three different types of electric fields. One is that if you attach these to the two of the shorter sides, you get an electric voltage E. If you attach these to the two of the longer sides, you get another electric field E2. And if you attach these across, then you get another electric field which is E3. So thus E1, E2 and E3, the three type of voltage generation is possible from a piezoelectric material. So let us look into now the stress-strain relationship, or in other words the constitutive equation of piezoelectricity. The stress-strain relationship that you have here, you may not be able to readily identify it because we have changed the symbols and we have made it compatible with the IEEE way of writing these symbols. However, if I just tell you that the first part of the second equation, if you look at it, x is strain, so you know that you generally show it as epsilon. In this case it is not, in this case epsilon is permittivity, but generally you say that epsilon equals to S sigma. That means the sigma is the x and epsilon is the small x here. Capital X and small x are the small strain and the are the strain and the stress in the material. Now with this relationship, you know that this is nothing but the Hooke's law, right, in one form or the other. So the first part of the second equation is actually the Hooke's law. The only thing that is added here that made it functional, made it smart, is that if you add the electric field E, in fact E by definition is actually voltage across the thickness V over T. So if you apply the electric field, because of the coupling factor D, small d is known as the piezoelectric constant, you are going to generate strain in the system. So this is an extension of the Hooke's law, which is covered by the converse effect of piezoelectricity. Now let us look at the first equation, which is actually discovered earlier, that is the direct effect. In this case, once again, if you initially do not consider this part, then what you are going to get is actually the standard relationship for a capacitor, because you know that the electric field displacement D, that's the electric field displacement of a capacitor, that is proportional to the electric field that you are going to apply, and also the permittivity of the field that I had already discussed. So this part is a standard equation of the dielectric material. The addition of the dx part, where actually once again capital X is the stress and small d is the electromechanical coupling coefficient or piezoelectric constant, that actually says that yes, you can generate charge not only by applying a voltage but also by applying stress. That's what is the direct effect. So you have two different effects defined by two different equations, in which part of the equations are already known to you. It's this additional part which, when we are considering, we are getting the effect of the piezoelectricity. Now there are various ways in which we can actually define this piezoelectric effect in the direct effect and the reverse effect. What is positive, what is negative? One of the convention is like this, that suppose this is my direction of polarization, that means I have a black spot here, and then if I apply actually compressive stress along this polarization direction, then it will generate a voltage of the same polarity as the Pauling voltage. So if this is plus and minus, it will generate the same voltage, same polarity of the voltage. On the other hand, if I apply the same compressive stress not in this direction but in the perpendicular direction, then you are going to get voltage of opposite polarity, because now it is minus in the top and plus in the bottom. Extending the same logic, instead of compression, if you give here tensile stress which is opposing the direction of actually polarization, then naturally you will generate a voltage which is opposite to that of the Pauling voltage. And in that case, if you apply the tensile stress in the perpendicular direction to the polarization, then what you are going to get is a voltage which is of the same polarity as the Pauling voltage. So these two cases are just an extension of the first two logics. If you keep that in mind, that compression matched, direction of compression matched with the direction of polarization are going to give you positive voltage, and if it is perpendicular, it is going to give you a negative voltage. And in the case of tension, if it is opposite to the direction of polarization, it is going to give you a negative voltage. If it is towards the in the perpendicular direction tensile stress, it is going to give you the same effect as the direction of polarization. Now for the converse piezoelectric effect, where you are interested in deforming the system, there what will happen? If I apply plus and minus following the direction of polarization, then what I am going to get is that voltage of the same polarity as the Pauling voltage. It will cause an extension along the Pauling direction, so it is going to expand. On the other hand, voltage of opposite polarity as the Pauling voltage will cause a contraction in the system. So that is how we will get the direct and the converse effect of piezoelectricity. Now, again and again here, one particular constant is coming. That constant is electromechanical coupling coefficient or piezoelectric constant. Now, that constant can be defined in two ways, because you have two equations where this d was there, right? If you remember, if I go back once again, you just see that in the first equation you have d, small d, and in the second equation also you have small d. So, if we see that there are two ways of defining it, the first one says that charge generated in the k direction, the dki, charge generated in k direction over when you are applying mechanical stress in I direction. That is one measure of D. The other measure of D is that when you are applying electric field in the k direction and you are getting strain in the I direction. So, in one case then the unit is Coulomb per Newton, and in the other case the unit is meter per volt. The same constant, that is very interesting, can be actually described with the help of two different unit systems. Now, it is not only this coupling coefficient D that is important, the piezoelectric coefficient D that is important. There is the electromechanical coupling coefficient which is even more important, and it basically talks about the ratio of the two energy, that is mechanical energy stored in direction j over electrical energy applied in direction I, or the other way, vice versa. So, that actually tells how much of energy is getting transformed from the system. So, that is even more important consideration. In fact, coupling coefficient and the electromechanical constants, they are actually related to each other. Now, how do we prepare a piezoceramic actuator? Very simple. We first start with a fine powder of its component metal oxides, because you have to go to a tertiary, like three element system, AbO3s. So, you, for example, for lead zirconate titanate, you start with lead oxide, zirconium oxide and titanium dioxide powders. Mix them in fixed proportions. Use an organic binder, otherwise they will get lost. Form into specific shapes, make them in a specific shape, we call it that, give the green shape, and then heat for a specific time and temperature about 650 to 800 degrees centigrade. Cool it, apply electrode layers using sputtering, polarize the sensor actuator using a DC electric field. Your piezoceramic actuator is ready for use. Okay, so once again we have to first take all the basic oxide powders, lead oxide, zirconia, titanium oxide, and then mix them, use organic binder, apply temperature and pressure in a particular shape, and then cool it, apply the electrodes. Your material is ready to be used. Now, there are many ways in which you can make the powders, of course. You can use solid state reaction, co-precipitation, sol gels, which does not need heat, so spray pyrolysis, emulsion synthesis, hydrothermal synthesis. There are many ways in which you can do the powder. Also the shape forming, you can use pressing, you can use casting, plastic forming, colloidal processing, so that you can give the required shape of the actuator. High temperature sintering can be pressureless, can be using hot press, can be using hot isostatic press. Finally, finishing is very important because it is ceramic material. So, this finishing could be mechanical. In that case, you may not get a good finish. It can be laser, water jet or ultrasonic. Ultrasonic is one of the best finish that you can get out of the system. So, thus you can actually make a piezoelectric actuator. If I now compare the properties of some of the common piezoelectric actuators, for example, barium titanate, you look at their D31, it is 79 picocoulomb per Newton. Compare that with lead zirconate titanate, you can get the highest of 234 picocoulomb per Newton. And lithium niobiums, etc., they are very small, but possibly they work at a higher temperature, which is what is good for them. So, this is an overall comparison of the piezoelectric material property set. Now, a few observations you can actually have from this comparison. One is that PZT family has the highest piezoelectric coupling. Actually, it is not entirely true, but in a polycrystalline phase it is true. In terms of a single crystal, PMN may give actually even higher, and the K33 value for PMN is about 0.92 and D33 is about 2070 picocoulomb per Newton. So this is possibly the best one. The Curie temperature of lead zirconate family is about 220 to 315 degrees centigrade, and for lithium family about 600 to 1200 degrees centigrade. This extreme temperature resistance capability, because you see beyond Curie point the material is going to lose its property. So this extreme temperature resistance capability makes these lithium families like lithium niobiums etc. to be very good candidate smart materials for applications like batteries, your laptop battery and things like that. Now make a piezoelectric polymer so that I can give better shape. You can get a piezoelectric material itself which has kind of asymmetric distribution from the long chain molecules with the repeat unit of CF2CH2, and these pendants of fluorine is what actually makes it piezoelectric. There are various forms. Form 1 PVDF shows all trans, then cis trans etc. The D3 one that you can get is not very high, at most about 19 picocoulomb per Newton. K31 is about at most 14.7%, but the modulus of elasticity is 1.6 to 3.8, which means it's pretty flexible. And with that flexibility, if you use it, you can actually make good use of such a system as sensors. You can also make composites in which you can keep a polymer, any polymer and PZT powder. This is even better than a pure polymeric system, and you can make smaller particles of lead zirconate titanate for example and then put it in PU matrix, and sometimes larger particles are also put in silicon rubber matrix. It has been shown by Skinner et al. That by using a special kind of a configuration you can get a very high connectivity, and this composite can ultimately become a very good transducer material. Now there are various applications of it. One is called a D31 actuator of piezoelectric material. In this actually what happens is you are applying the current along the three direction. This is the three direction I have already shown, and you are getting the force or the deformation in anywhere along the one or two direction. The sensor does the same thing, but in this case instead of the stress it has to sense the displacement and then convert it in terms of the voltage. Now this can be done in another manner. It can be done as a stack also. So what you can do in such case is that you apply the voltage over the electrodes, and in the same plane you take the force out. This is what is called piezoelectric stacks, and this can be done as actuator, this can be also done as sensor. So there are various combinations that you can play. So this is where we will stop today. In the next lecture I am going to talk about magnetostrictive materials, their constitutive equations and different effects of magnetostriction. Thank you.